Okay, this is Jack Jackson. This is the last of this series of derivative problems, 20 problems where we're trying to find the derivative and the tangent line at y equals 1. And we've been finding the second derivative, but let's don't worry about the second derivative this time. Look at this particular function here and see if you can find the derivative formula for it. If you haven't done so, go ahead and do it now. Press pause. Well, notice that this is not a constant to a variable power, which would be the exponential rule, or nor is it a variable base to a constant power, which would be the power rule. So we have to use either the technique of logarithmic differentiation or the result that we got from using that technique, which is called the generalized power exponential rule, which is actually how we ended up proving the power rule. So to do this derivative, we're going to use that. So we think of it as basically like it's a power rule and an exponential rule added together is what it boils down to. So we basically apply the power rule first. So we take the old power, multiply it out front, keep the same base, and subtract 1 from the power. Subtracting 1 from the power makes the new power 3x squared minus 5. Then we have to apply the chain rule and say take the derivative of that base, which is 5, plus. Now we treat it as if it were an exponential function. Exponential function, you take the logarithm of the base times the original function just like it is, but then we also have to multiply by the derivative of that power. And the derivative of the power is 6x. And so there's the derivative right there. We're just going to clean it up a bit. Notice we're going to factor out a 5x to the 3x squared minus 5. And this goes away, and so you've got 5 times the 3x squared minus 4. Here, when you factor that out, factor this out, you would get this to, that's one smaller power than this. So we're left with the 5x to the first power. So 5x to the first power times this will give you 5x to the first power times 5x to the 3x minus 5 power gives you what we have, which is 5x to the 3x squared minus 4. So we get this, we still got our 6x. Now notice these both still have a 5, so I'm going to go ahead and factor that out as well. Well, I'll do that in a minute, it looks like. So I distributed it first, 5x squared minus 20. This is 30x squared times ln of 5x. And then I noticed they both had a 5, so I factored that out front. Could have done it earlier, but I did it here. And then what does that leave? Well, let's see, divide this by 5, we get 3x squared. That's here at the end. And negative 20 divided by 5 is negative 4, that's here. And divide 30 by 5, that's 6, and then we got the x squared and the ln of 5x. So that's one way to write the derivative formula there. We can check it. Put the original function right here, 5x in parentheses to the power of 3x squared minus 4. Be sure you put parentheses around the power and the base, both. Turn that one off. Let y2 be the derivative of y1 with respect to x evaluated at x. Here's our final answer, the way I put it in here. Check to see if the tables for y2 and y3 work, and they are just fine. Okay, and so that's what we end up with there. Notice we do get some error messages on the outsides here. I think the error message here on this part is not because it's not defined, it's just because it grows so fast that this becomes too big for the calculator to handle. The error message over here is a problem because if we have a 0 base to a negative power, so for example if you try to put it in 0, we get 0 to a negative 4 power, that's undefined. And we're not going to try to see what would happen with a negative base to a power, although those are defined for certain powers. For certain other ones, certain other values there, it would definitely be undefined, and so certainly the derivative is undefined for 0 and negatives. So it looks like, at least as far as the derivative goes, this should be from 0 to infinity. So there's a vertical asymptote there, and even though the original graph might have some isolated points over here that's defined, we're only going to really look at it over here in the first quadrant. So you might as well just assume that x is positive here. Okay, So let's look at the tangent line. If we let x be 1 in the original one, we get this. Let's see what that turns out to be. 1 squared is 1 times 3 is 3, minus 4 is negative 1, 5 times 1 is 5, 5 to the negative 1 is 1/5. So 1 comma 1/5 is a point that's on there. So we have x minus 1 here, we have plus 1/5. We need the slope. The slope is the derivative with the 1 in place there. So take this derivative, put 1 in place there. A lot of canceling going on here. Once again, let's see, 1 squared is 1 times 3 is 3 minus 5 is negative 2, so that's a negative 2 power. The base is 5. We have the 5 out here. Here we have, this is just 6 log of 5 plus 3 minus 4. 3 minus 4 is negative 1. 5 over 5, that's 5. This should be, let me look at that again here. 5 times 5 to the negative 2 is 1 over 5, that should say. And I hope I have this thing graphed right. It's going to be hard to tell the difference, actually. But it should go through the point 1/5, and then this should be the slope right there, and so it should come along. Looks pretty good. I'm not sure if I have the right one graphed or not. But it looks very similar to that at least. Here's the original function here. Notice that the derivative is, we're going to define it only for positives, but notice this is a quadratic here, and it had, well, it's not really, it's got an ln in it too. So it's a more complicated function, but it looks like it actually has a place where it crosses the x-axis somewhere in here. So the original function goes from decreasing to increasing. The second derivative, I didn't work it out here, but I have a graph of it here. Notice the second derivative is always positive, so the original function is always concave up, and the derivative is always increasing. So there we have that example worked out. Okay, so now at this point, we have seen all of the how to do derivatives of let's see, what do we know how to do? We know how to do the constant multiple rule, the sum rule, the product rule, the quotient rule, a generalized version of the product rule, exponential functions, power functions, a generalized exponential power thing where we have variable base to variable power. We know how to do the chain rule, so we can do polynomials, rational functions, linear functions, logarithmic functions also. So basically all the functions that you really mainly study in your algebra classes. So in survey of calculus, this would be the complete list of functions that we want to find derivatives of. We started with some easy examples, and now we've gone to some much more difficult ones here. So we've seen how to do those. Now, the next step is to go on and start talking about trigonometric functions and inverse trigonometric functions and hyperbolic functions even. And so in Calculus 1, we'll look at those. But we will not be responsible for those in the survey of calculus class.